Okay, so in this part of the lecture, we're going to start talking about reciprocals via Fermat's little theorem. And so last time we ended sort of abruptly because of a fire alarm, and we didn't really finish up that part of the lecture. So I'm going to take some time and review the sort of punchline of Fermat's little theorem, which we were talking about on Monday, as well as one application of them, which is another way of computing reciprocals. So let's remind ourselves of what Fermat's little theorem is. So, well, we're going to let P be prime, of course, because Fermat's little theorem only works when you have prime modulus. And then if x is not congruent to 0, then x to the p minus 1 is congruent to 1 mod p. Another way of saying this is you could also say that for any x, including 0, x to the p is congruent to x mod p, which is a really cool little result and turns out to be super helpful in computing really large powers. So for example, 12 to the 22 mod 23, well, that's just congruent to 1. So you immediately know that because 23 is primed. Or 12 to the 23 mod 23 is equivalent to 12. Oh, why is it called Fermat's little theorem? Because Fermat wrote a bunch of theorems down, and people had to give them lots of different names. I don't actually know why this one in particular is called little. Some of you may have heard of Fermat's last theorem, and that was only proven in the 90s. So he wrote down some theorem that he thought was correct. His proof was probably wrong. He didn't even actually write down our proof. It was just like, oh, look at this fun fact. But yeah, so Fermat wrote down a lot of these facts, and so the important ones were given names. Some of them weren't given names. This one is sufficiently helpful, but the proof is also sufficiently easy that it was just called his little theorem. Like, you'll notice that we actually did the proof last time on Monday. So we actually went through a rough sketch of this proof, and it's not, as proofs go, it's not a super complicated proof. Yeah. Okay, but yeah, so with Fermat's little theorem, this basically lets you quickly show that some power is congruent to 1. So just as a quick reminder, in mod p, p is congruent to 0 mod p, right? So we already all knew that. That's sort of the basics of modular arithmetic. The other thing we now say is x to the p is congruent to p to x mod p. Okay, so somehow there's the specialness around p or p minus 1 and 0. And this turns out to actually have some deep connections in higher algebra, but we're not going to talk about them so much in this class. We're just going to talk about how we can use Fermat's little theorem to quickly reduce large powers by division of remainder. So notice that if n divided by p minus 1 has a remainder of r, then x to the n is congruent to x to the r mod p. What do we mean by that? Yes, this is used for modular. So 14 to the 444 mod 23. Well, what's that equal to? Well, what you can do is you can just take 444 divided by 22, not 23, divided by 22. So that gives you 20. So that's 440, remainder 4. So that is congruent to 14 to the 4 mod 23. So you might notice that what this implies is that if p is prime, then, well, obviously you're using mod p arithmetic when you're just like adding or multiplying, right? But also somehow the exponents behave according to mod p minus 1 arithmetic. So try not to get too confused by that, but the key point here is that x to the p minus 1 is congruent to 1 mod p, when p is prime. And so what we're doing here is you're basically saying 14 to the 4 is congruent to 14 to the 22 plus 4 is congruent to 14 to the 22 plus 22 plus 4, and so on. Okay, and let's try it out since we got interrupted in trying it out last time by a fire alarm. So let's try it out. What's 4 to the 244 mod 7? So now, of course, you could do this by using powers of 2 and just like breaking up 244 into 128 plus 64 plus so on. But we now have an easier way of doing it. That only works, mind you, when P is prime. And of course, you all have a homework assignment that's due on Friday. And there are some really, really large powers in prime modulus that you guys need to do. And this is one way of doing them. Okay, we're starting to get a few answers. We're getting a lot of A's, a few C's. So let's try to figure it out. So first, what are we dividing by? So if we take 244, what are we dividing by? Yes, 6. 7 minus 1 is 6. Don't divide by 7. If you divide by 7, it won't work. So, well, dividing this, that's a 4, 24, 0, 4, 40, remainder 4. So this is congruent to 4 to the 4 mod 7. Well, 4 to the 1 is congruent to 4. 4 squared is congruent to 16, which is congruent to 2 mod 7. And 4 to the 4 is congruent to 4. And so this entire thing is congruent to just 4 mod 7. So the answer is indeed A. Okay. Yeah, no. So that's one of the reasons I'm having you guys try this out. The key here is that you need to divide by 6 for the exponent. But then when you're doing this here, this is all mod 7. So 16, you need to this 16 here, you're dividing by 7 to get a remainder of 2. And so just be careful that about when you're dividing by 6 and when you're dividing by 7. Okay, let's have you all try another one. 7 to the 286 mod 13. So again, you have to be a little bit careful about what you're dividing by. Sometimes you'll be dividing by 13, and sometimes you'll be dividing by 12. And you just need to make sure that you're always clear on which one you're doing. And if you're ever confused about which one you're doing, basically when you're using Fermat's little theorem, you're dividing by P minus 1. When you're doing just ordinary modular arithmetic, then you're dividing by P. So when you're dividing the power, the exponent, then you're dividing by P minus 1. Seeing an and in the chat. Oh, can I repeat that? Yes. So notice that there are two things that you need to be careful about. So first, let me do this in a different color. P is congruent to 0 mod P, right? And so normally, in order to get mod P, you divide by P and look at the remainder. But x to the P minus 1 is congruent to 1 mod P. And so basically what you're doing is that means that in the exponent, you can keep on subtracting out by P minus 1. And so in the exponent, if you find the remainder with respect to P minus 1. Okay, so we're getting a few answers. Let's start working through it. Hopefully I did this right, because it seems like a lot of people are getting E, which is not what I actually got. So let's work it through together. And so please double check me as we're doing this. So hopefully I didn't do this wrong. So 286 divided by 12, right? Because you're taking the exponent, you're dividing by 12 and finding the remainder. That's 2, that's 24, 46. Well, what's 46 divided by 12? Well, that's 3, so that's 36, remainder 10. Okay, so this entire thing is congruent to 7 to the 10 mod 13, right? Okay, well, what does that equal to? Well, that's if you break it up. So unfortunately, you do need to use the powers of 2 method once you've found this stage to figure out what that actually is. Or you can just multiply 10 times, and that will also get you an answer. What I'm going to do, this is 7 to the 8 times 7 squared, right? And the question is, what is 7 to the 8 and 7 squared? Well, 7 to the 1 is congruent to 7. 7 squared is congruent to 49, which is congruent to, what is 49 congruent to? Divided by 13, 13 times 3 is 39, so this is congruent to 10. Then 7 to the 4th is congruent to 100. Well, what's 100 congruent to? 13 times 7 is, that's 21 and 7, so that's 91. This is congruent to 9. And 7 to the 8 is congruent to 81. And 81, well, 13 times 6 is going to be equal to 1, so that's 78. Oh, yeah, so you may be able to brute force some of these numbers with a good enough calculator, but you may not, and so sometimes it'll work and sometimes it won't. So that's a 3, and so this entire thing is congruent to 3 times 7 mod 13, which is congruent to 21 mod, no, not 3 times 7, 7 squared. So you need to, that's congruent to 3 times 10 mod 13, which is congruent to 30 mod 13, which is congruent to 4 mod 13. Okay, so you still do need to take a reasonably large power, but it won't be as large as it would have been if you had just tried to do the entire method for 7 to the 286. So this is a shortcut when you have really, really big powers, because division is a lot easier than the sort of binary power expansion thing. How do you know to break 7 to the 10 into 7 to the 8 and 7 to the 2? So the real answer is you can break it into whatever you want. The less flippant answer is, I find one easy way that will always, one straightforward way that will always work is to break it up into the highest powers of 2 that you can. So remember, on some previous slide, I showed you a bunch of powers of 2. If you break it up and subtract out 8, and then you're left with 2, which is the power of 2, and so you break it up into 8 and 2. Well, why didn't we stop at 7 to the 49 is 7 squared is congruent to 49 is congruent to 10. Oh, so this piece gave us this piece, but then we also still needed to figure out. So if you wanted to, you could get 7 squared is congruent to 10, and then do 5 of those. So another thing you could have tried is you could have also said that that's congruent to 10 to the 5 mod 13, and that would also be true. So you can do it all these other ways. You can also do 7 to the 5 times 7 to the 5, and that will also give you the right answer. And if you don't believe me, you should check that yourself. All of these things will give you the right answer. The question is, which one do you want to do? I gave you the method for breaking it up into powers of 2 because that will consistently work. But if you see the number and you're like, oh, well, it's easier for me to break it up into these other factors, then you are also free to do that. Yep. Yeah, so you can do 7 to the 5 times 7 to the 5. It will also work. Sometimes it'll be easier, and you're allowed to do these other methods, but it just isn't an algorithm that will work every single time. Whereas breaking it up into powers of 2 will always work, but sometimes it'll be more work. Okay, so let's have you all do one more example. What about 3 to the 401 mod 81? And I'll be curious to see what people get. Okay, so it looks like we're getting a lot of D for 3 to the 401 mod 81 is equal to 3. How do you guys get that? Well, let's take a quick look at this. So my guess is that you guys did this by saying, well, 3 to the 401 is congruent to 3 to the 80 times 5 plus 1, right? Which is congruent to 3 and to the 1, which is congruent to 3. That is wrong. Why is this wrong? It's not prime. 81 is not a prime number. This Fermat's little theorem only works when you're working with a prime number. And so that does not work. And so if you were going to do this, you would have to do it some other way. It turns out that the correct answer here, well, you might notice that 3 to the 1 is congruent to 3. 3 squared is congruent to 9. 3 to the 4th is congruent to 81, which is congruent to 0. So 3 to the 401 is congruent to 3 to the 397 times 3 to the 4th, which is congruent to 0. So the answer here is actually A. So one of the things you have to be really careful about with these more advanced methods is sometimes they depend on some particular fact about your numbers. And if they aren't prime to begin, if your modulus isn't prime to begin with, Fermat's little theorem is incorrect. It does not hold. And so you can't just throw numbers into this algorithm. You have to actually sit down and identify and make sure that the conditions for the algorithm were all correct. Just a moment. So how do you test if it's prime? Well, for numbers between 1 and 100, I will be giving you a list of primes, remember? And so, okay, but how do you test if a number in general is prime? Well, you have the sieve of Eratosthenes, right? So I made you guys test prime numbers like way back when. If I give you a very big number, you might have to use a more complicated, you might have to actually test whether it's prime or not. Remember, you only have to test up to the square root of that number to figure out if it's prime. But in this case, 81, well, one, you should know from your times tables that 81 is not prime. And two, if I give you a list of primes, you can check to see that 81 is not there. But yeah, so be really careful because sometimes I give you these methods and they only work when one of your numbers is prime, or maybe two numbers are relatively prime, or other conditions like that. And you do need to check. And there will be examples on your final exam where I give you problems like this, and it is up to you, it is incumbent on you to realize that the standard method does not work. Oh, well, why is this equal to 0? Well, this is equal to 3 to the 397, but remember, 3 to the 4 is equal to 0, so times 0, which is congruent to 0. So remember how when I made you guys do the powers tables? What was it? 6 squared in mod 12, 6 squared, and any power of 6 beyond that was just 0, because 12 was not prime. In this case, 81 is not prime, and so there happen to be some examples of numbers where all of a sudden you get zeros. So 3 to any power greater than or equal to 4 is equal to 0. Okay. So having left you with that warning, so always check the conditions. So if I say that something has to be prime to work, you need to check that it's prime, because if it's not prime, it won't work. What if the power is divisible by the mod? No. Remember, part of Fermat's little theorem is that 3 to the p is congruent to 3 mod p. And clearly p is divisible by p, right? So what you have to remember is that for the powers, you're dividing by and finding the remainder with respect to p minus 1. And if the modulus is prime, then you won't ever get 0 as a power. Because remember, the powers repeat. And if you ever got a 0, well, then they'd all be 0 for the rest of it. So this can only happen if you have a composite modulus. Okay, so let's keep on going. So be careful when you're doing this. I'm going to point out some other cool stuff you can do with things like Fermat's little theorem. And I'm going to give you an alternative way to find reciprocals. So remember, there's the ordinary way of finding reciprocals. So for example, 1/5 mod 11. Well, you use the Euclidean algorithm to find 11 is equal to 5 times 2 plus 1. 5 is equal to 5 times 1. And so this implies that 1 is equal to 11 minus 5 times 2, or 1 is congruent to minus 5 times 2 mod 11. So then 1 divided by 5 is congruent to minus 2 mod 11, which is congruent to 9 mod 11. Okay, so this is the Euclidean algorithm for finding reciprocals. Oh, it looks like we have a question about, why is n 0 when n is more than or equal to 4? I suggest you just write out all of, so remember, you know how to write out all the powers. So we did that on the, I think that was on your midterm, right? So I made you write out all the powers of a number on your midterm. Try doing that with mod 81. And you will find that they're just all equal to 0 after 3 to the 4, because you're just constantly multiplying 0 by 3. But anyway, we had this other way of doing, we had this way of finding reciprocals. And it's not too bad. You just use the Euclidean algorithm, and then you solve for that, and you get the reciprocal. It turns out there's another way of doing it, which is sometimes harder and is sometimes easier. So sometimes you want to use it, and sometimes you won't, which is to use Fermat's little theorem. So notice, if you're in a prime power, so this has to be prime. So prime. Then x to the p minus 1 is equal to, is congruent to 1, right? Well, if that's true, and we're in a prime modulus, that means you can divide by x on both sides, right? So if you divide by x on both sides, you get x to the p minus 2. It's congruent to 1 over x mod p. Right? Because you're in a prime modulus, so you're allowed to do division. Another way to think about it is if I know that if I multiply together p minus 1 copies of x, you get 1. So if you have p minus 2 copies, and then you multiply another copy of p, then you're also going to get 1. And so those multiply together to give 1. And so x to the p minus 2 is the reciprocal of 1 over x. Or sorry, is the reciprocal 1 over x. Why is it minus 2 and not minus 10? Oh, because here, divide by 5 on both sides, right? So remember, when you're working with a prime modulus, you're allowed to do division. And that's basically what I've done here. So because I'm allowed to use a prime modulus, I'm allowed to divide by 5 on both sides. Okay, but anyway, we have this other way of figuring it out, of finding reciprocals. It will often be harder. Let me just go ahead and say that. But sometimes it'll be easier. But let's try it out for this same example. So what is 5 to the 10? Oh, sorry. We know that 5 to the 10 is congruent to 1 mod 11, right? And that's just Fermat's little theorem. So we just know that to be true. So that means that 5 times 5 to the 9 is congruent to 1 mod 11, which means that 1 over 5 is congruent to 5 to the 9 mod 11. So that's another way of finding a reciprocal, which is you just multiply together powers of 5 until you get to almost get back to 1. So 5 to the 1 is congruent to 5. 5 squared is congruent to 25, which is congruent to 3. 5 to the 4 is congruent to 9. 5 to the 8 is congruent to 81, which is congruent to 4. And so then therefore 5 to the 9 is congruent to 5 to the 8 times 5, which is congruent to 4 times 5, which is congruent to 20, which is congruent to 9 mod 11. Depending on which one you're more comfortable with, you may want to choose to find reciprocals one way or the other. But now you have two completely separate ways of finding reciprocals in prime moduli. So let's have you all try it out. Let's see. So find 1 divided by 12, mod 67. And I'm hoping that to have you all do this using the method of Fermat's little theorem. I know you can also do it using the Euclidean algorithm. You should practice both. But for this particular case, I'm asking you to try it this other way. Another thing you should do, once you've found your answer, you should check if it's right. How do you check if an answer is right? Well, you multiply it by a number by its reciprocal. So multiply 12 by whatever number you find as reciprocal, and that should give you 1. And if it doesn't give you 1, then you did something wrong. So, for example, if I take 20 and I multiply it by 12, if 20 were the reciprocal of 12, then that should be equal to 1 mod 67. Is that equal to 1 mod 67? And if it is not equal to 1 mod 67, then A is incorrect. So that's one of the key points that I really want to emphasize, especially on exams where I give you enough time. You should be double checking your answers. So here I'm computing the reciprocal of 12. And that means that whatever answer you get, if you multiply by 12, you should get 1. And you'll notice that this gives you 240, which if you divide by 67, that's 3. So that's 21 and 18. So that's 20. So that gives you 39, remainder 39. So it is not A. So A is incorrect here. Okay, so let's try to solve this together, since it seems like a lot of people put down A and are a little bit confused about what's going on. So 12 to the 66 is congruent to 1, right? That is Fermat's little theorem. And therefore, 12 to the 65 is congruent to 1 over 12. Well, and what's 12 to the 65? That's just congruent to 12 to the 64 times 12. And so now what we have to do is we need to find 12 to the 64. So we can do that. So 12 to the 1 is congruent to 12. 12 squared is congruent to 144. 144 should be congruent to, well, 67 times 2 is 120, 134. So this is congruent to 10. Then 12 to the 4th is congruent to 100, which is congruent to, well, 67. 100 minus 67 is 33. Then 12 to the 8th is congruent to, what's 33 squared? I think I have written down 1089. Hopefully that's correct. And when you take this to division by 67 and find the remainder, you should get 17, and so on. So I wrote down these numbers beforehand, since I don't have a calculator on hand right now. So if you keep on going, and this is a little bit painful, but you can keep on going, and you should get that this is congruent to 47 times 12, which is congruent to 564, which is congruent to 28. Okay, so this is a little bit painful, but once you have the answer, you should be able to double check. So what's 28 times 12? well, 28 times 12, that's 56, and that's 28. So that's 336, right? And what's 336 divided by 67? So that's 1, 2, 3, 4, 5. So that gives you 335. So that's remainder 1. And so it is indeed 28. The other way to solve this would have been to use the Euclidean algorithm, and you should get the same answer either way. Regardless of what answer you get, you should multiply it back to double check your answer. Okay, so what didn't turn out so well? Let's try another one. So I'm going to ask you to find 1/2 mod 131. And I'm going to go ahead and say you can do this either way. You can either do this using Fermat's little theorem, or you can do this using the Euclidean algorithm, whichever one you prefer. Because realistically, on the exam, you can generally use either, whichever one you find easier. I'm going to start going ahead and giving you the setup for using Fermat's little theorem, since that's, of course, what we're trying to do in this part of lecture. So we'll have 2 to the 130 is congruent to 1 mod 131. And so therefore 2 to the 129 is congruent to 1/2 mod 131. So now we have to give out a bunch of powers of 2. 2 is congruent to 2. 2 to the 2 squared is congruent to 4. 2 to the 4th is congruent to 16. 2 to the 8th is congruent to 256, which is congruent to 125, which is congruent to -6, just to make life a little easier. And 2 to the 16 is congruent to 36. 2 to the 32 is congruent to 1296, which is congruent to 1296 minus 1310, which is congruent to -14. And 2 to the 64 is congruent to 196, which is congruent to 65. And 2 to the 128 is congruent to 4225, which is congruent to 33. Okay, so given all of these powers of 2, hopefully you can solve for the reciprocal. Yeah, good. So this is congruent to 33 times, oh wait, 33 times 2. So the answer here is actually 66 mod 131. And for all of you guys who put down 33, you should be double checking your answer. So what's 33 times 2? Is 33 times 2 equal to 1? So importantly, you should be double checking your answer. 66 times 2 is congruent to 132, which is congruent to 1 mod 131. So you should be checking your answer. And honestly, if someone were to give you a multiple choice question, the thing to do would just be to multiply each of those numbers in and check to see if it's the reciprocal. Obviously, you won't be getting a multiple choice question like this on the exam, but if someone were to give you that, that would be the correct way of doing it. For the Euclidean algorithm, do we get it by doing? So for the Euclidean algorithm, let's also do it using the Euclidean algorithm, just so that we see it both ways. So for the Euclidean algorithm, what you do is 131 is equal to 2 times 65. Oh, wait, is that, no, not 65. No, 65, that's right. Plus 1. So then therefore, you know that 1 is equal to 131 minus 2 times 65. So 1 is congruent. Wait, I think I did that wrong. What did I do wrong? 131 is equal to 2 times 65 plus 1. Okay, so 1 is equal to 131 minus 2 times 65. Okay, so then 1 is congruent. Oh, so to, yes, so that's right. So that's congruent to minus 2 times 65. Divide both sides by 2. So 1 over 2 is congruent to minus 65. But of course, what is minus 65? Minus 65 is congruent to 66, mod 131. But yes, so you get it by taking minus 65 plus 131. Okay, and with that, I will give you all a proper break. So please be back at 10, let's say 14, and we'll go through the last part of today's lecture, the next part of today's lecture, which will be about roots and prime modulus arithmetic. So let's take an 8-minute break, and I'll see you all in a few minutes. Oh, if you leave the answer at 65, is it wrong? If you leave it at 65, it's wrong. If you leave it as minus 65, I will give you full credit. So remember, what I'm saying is that for the remainder of the class, for the next quizzes and the final exam, you're allowed to do either positive or negative, but it has to be the smallest positive or negative number. So you're allowed to leave it as the smallest negative number or the smallest positive number. By smallest, I mean smallest in magnitude. So if you leave it as minus 65, that's fine. But if you had left it as minus 196, then that would not be fine. Okay, anyways, have a break, and I will see you all in a few minutes.